Solids and unit cells. An unknown metal is found to have a density of 7.8748 grams per centimeters cubed and crystallize in a body standard cubic lattice. The edge of the unit cell is 0.28664 nanometers. Calculate the atomic mass of the metal. So we want grams over mole. That's what we're looking for here in the end. And we're told something about body-centered cubic lattice. So that's a body-centered cubic unit cell. So if we have a cube, it's not a good cube. Something like this is a little better. Okay, let's say we got this cube. So body center means that you have something in the center, and then you have these 8 corners filled. So you have 1/8 times 8, which gives you 1 atom, and then you have 1 atom in the middle. So you have 2 atoms in total per cell. So that's important when looking for the mass. Okay, so let's go through this piece by piece. The edge length is equal to 0.28664 nanometers. Since I'm given the density, I can isolate grams because I want grams over mole, getting rid of the centimeters cubed. So my first step is to take the length and convert to centimeter cubed, or centimeters first, I would say. So 0.28664 nanometers times 10 to the negative 9 meters, or however you want to convert, times 100 centimeters over 1 meter. So then my nanometers cancel on my meters, and I have 2.864 times 10 to the negative 8 centimeters. So all I've done is convert nanometers to meters. The reason I did that is because since I want in the end to have grams over mole, the only other piece of information in this question is the density that has grams. I need to get rid of what's on the bottom, which is centimeters cubed. So I have my centimeters, but I don't have it cubed yet. So volume is length cubed, so then I just cube that number. 2.864 times 10 to the negative 8 centimeters cubed, which is, if you plug that in, 2.349 times 10 to the negative 23rd centimeters cubed. Great. Now I can find my mass. So I take that volume and multiply it by the density. Then I get grams. 1.849 times 10 to the negative 22nd grams. Great. Now what's important to know is that we just found the mass, but that's per 2 atoms. Since it's a body-centered cubic cell, that's per 2 atoms because that's in the entire cell, and we used the density and length of the whole thing. So now to isolate for the grams and the moles, let's look at how we can do that. I have 1.849 times 10 to the negative 22nd grams over 2 atoms. Now again, up to this point, not too shabby, right? You have the length and density. You know that at one point you need to get grams over mole. Let's focus on the grams part first. Well, grams over centimeter cubes means you need to isolate for just grams. Get rid of the unit you don't want. The only piece of information you're given here is the length. A cube, right? You can find the volume by cubing that length. So we had to convert to the centimeters, cube it to get centimeters cubed. Then once multiplied to the density, you find your grams. Now here was the newer part, since this is a unit cell problem. Because of the 8 corners, there's 1 atom, and then in the center, there's another atom. So we have 2 atoms in this cell. Since we want the overall molar mass, atomic mass, we have to account for that. We just found the mass per 2 atoms. I want grams over mole. There's only one conversion factor I know that has particles, things over mole. That is Avogadro's number. So if I then multiply it by Avogadro's number, 6.022 times 10 to the 23rd atoms over 1 mole, my atoms cancel and I'm left with 55.86 grams per mole. And then that is my atomic mass. So it's important, a bunch of other stuff that we've already known used here, just knowing that it's per 2 atoms. Then getting the moles is going to another value we've used a lot, which was Avogadro's number. And this would have been able to do for face-centered cubic cells, simple cubic cell, just looking at how many atoms you have per that cell, because that's what the mass that you're looking for. An oxide of titanium crystallizes with the unit cells shown here. What is the formula of the oxide? We have titanium gray and oxygen red. Well, let's look at the oxygen first. I'm just going to look at the ones that I have on the outside, on the face. So I have 1, 2, 3, 4. I have 4. And if you see, really, really smally, they're all cut in half. So they're all contributing 1/2. So I have 4 times 1/2, which gives me 2 atoms of oxygen. But we can't forget about the other 2 inside. So these are completely inside. You can see that there's no separation. So I have also another 2 atoms of oxygen on the inside. So in total, I have 4 atoms of oxygen in this molecule. Now let's look at titanium. Now let's erase the oxygen notes. Titanium. I have 1, 2, 3, 4, 5, 6, 7, 8 on the corners. Now there's 8 corners, and I have 1/8 of them each, because there's only that one little spot of each that's contributing. So I take my 1/8, because that's how much that ball is actually contributing inside, just 1/8 of it, times 8 is equal to 1 atom. So each of the corner in total contributes to 1 atom. Now we can't forget about the one here in the middle, so then I have 1 more atom of titanium because it's in the center. So in total, I have 2 atoms of titanium. So if I put that together, metal's always written first, so Ti2O4. We write the lowest ratio, which will be titanium oxide, TiO.